Hi everyone, I am Michele Albano. I'm here to present the paper Kubernetes Scheduling for Green-powered Microgrid Data Centers, which reports on a research work done together with my students Simon and Loritz and my colleague Sam. We are from Aalborg University in Denmark. And the work was supported by the projects Green Code and MUST. Nowadays, data centers are consuming more and more energy, say for training AI, say for LLMs. In general, studies confirm that in 2010, more than 1% of global electricity usage was for data centers, and the prediction is that by 2030, data centers will eat between 3 and 13% of electricity. And doing efficiency is not very feasible since the power utilization efficiency is already close to 1%. So the idea here in this work is let's try to maximize the usage of locally produced energy, produced with renewable energy sources. So the objectives are to studying how to configure data centers as microgrids, so to let them operate both in connected mode and disconnected mode, where disconnected means that we don't use main grid energy, but instead we use energy produced locally with renewable energy sources or energy stored locally in the data center itself. And then the second objective is to study the benefits of doing this. So the benefit of doing opportunity computing over geo-localized microgrids. We will simulate microgrids over Europe and North Africa, considering not only the renewable energy, but also the environmental impact, the carbon footprint, of the energy that is used from the main grid. For example, you can see that in Germany, in Deutschland, we have here in the graph more renewable energies than in Iceland. But once the renewables are over, it's better to draw energy from Iceland since it's got a lower carbon footprint. We will use in this work Kubernetes. It's a leading open source orchestration tool that allows you to specify the workload in terms of pods, which are self-contained workloads. And then it allows you to configure them, scale them if you need more or less copies to perform the computation, self-heal if some of the pods crash, and also schedule, which in terms of Kubernetes, it means deciding where to execute the workload, on which computational node. Kubernetes natively does not support prioritizing energy sources, for example, renewable energy, but it's very customizable. Specific goals. In this work, we extended the industry leader Python microgrid simulator, which is a simulator for microgrids, to allow it to simulate a new kind of appliance, the computing node, which is node that, based on external factors, draw more or less energy. And then we extended the scheduler of Kubernetes using plugins so that this appliance can actually decide, the computing node, to consume energy based on what scheduler decides. So if the node is executing a job, the node will consume more energy. We will simulate different strategies. One that prioritize nodes having renewable energy available and battery charge. The second will be a trade-off between strategy one and considering the carbon intensity of the energy in the main grid. The evaluation will be done on using a real workload trace from Azure with around 170,000 jobs, and we simulate one microgrid per European and North Africa climate region. In total, 152 microgrids, each one with 6 computational nodes. Okay, microgrid configuration. All microgrids have the same configuration. All of them use photovoltaic panels to produce energy, and we'll use real solar data for each climate region. Each microgrid has got a battery module, and it's dimensioned to allow for a maximum capacity that corresponds to having a computational job of 10 hours being completed, since the size of the maximum job in the workload trace we are using. Initially, the total charge of the batteries will be 50%. And finally, the node module will scale the energy draw with CPU utilization based on the figure you see here, based on Dell's specification. For example, if you're using 10% of the CPU, you're consuming 140 watt. If you're using 70%, you're consuming 330 watts. System architecture. We have our simulator, and we have Quark, which is Kubernetes without Kubernetes. The idea is that we don't really execute a workload. We have a node saying, I am executing a workload, producing a number telling how much energy it's consuming, but actually it's event oriented. So what happens is that it will just output what's happening. This way, we are able to speed up the simulation. We will have the scheduler plugin for Kubernetes. Next slide. And we have a database that through a Flask API will store all the logs. And finally, we have the worktrace runner. You can see in the figure the number of virtual machines that are required to execute jobs based on the worktrace. The worktrace contains when any job starts and ends. That for us is the length of the workload, the CPU usage, and we will execute only one job per node. And in total, we have, you can see in the graph how many hours. In total, we have 1 week of jobs. Scheduler plugin. Kubernetes allows you, using the Kubernetes scheduling framework, allows you to define custom actions that are executed by interrogating a certain API using get, post. And in particular, we decided to act not on the filtering step, where Kubernetes decides to exclude a set of nodes from the scheduling operation, but only on the scoring and the post-bind steps. The scoring is I take the nodes that are not removed by the filtering operation, and I decide which is the best for executing a job, and the post-bind is activated after everything is said and done. This way, we can put a high weight to our plugin so that Kubernetes will take decisions based on available renewable energy, carbon footprint, and grid, but we keep all the default plugins so that if two different nodes are similar in terms of, for example, renewable energy, other default strategies of Kubernetes will take place. And in the post-bind step, the scheduler will send back to the microgrid simulator the taken decisions. Results. When we use strategy one, actually we are able to shed a lot of workloads from the climate regions with less renewables to the ones with more renewables. You can see here the total difference among different climate regions. So among the microgrids simulated in the climate regions. You can see, for example, that Egypt is having 10% more load. The result is that we self-consume 35% more energy. If you use strategy 2, that takes into account and gives some priority to the carbon footprint of the energy in the local main grid, well, the result is that we self-consume close to 9% less energy. What about carbon footprint? Well, strategy two, since it limits the execution of jobs powered by the local main grid only to microgrids, where the main grid is quite green in terms of carbon footprint, well, the result is that we save 98.5% of carbon footprint. Wow, that's incredible. In fact, we did a little bit more investigation, and if you consider the idle nodes, the improvement is quite marginal. If we don't switch off any node when they're not used, we just save less than 1% of the carbon footprint. You can see here in the slide um, how much difference we have in total CO production in the different country codes. So, takeaways. Actually, using geographical diversity can increase renewable energy utilization and lower carbon footprint, which is a plus. However, the best case scenario is naive, since it's considering that no energy consumed in idle state, while actually the idle state consumes energy. Energy production is forecast in a perfect manner. We know how much available energy is in each microgrid, so we don't have any impromptu appliance switched on, for example, the internet student brewing a coffee, and the length of the jobs is predicted. All the data we have is available in the Jupyter notebooks at this QR code. So, future investigations. We have two investigations we are completing in December, January, and then we have future investigations. The current one is to automatize switching on and off the nodes. Because as we saw, the difference between the best case scenario and the worst case scenario for carbon footprint is the energy consumed by idle nodes. So we will switch off the nodes using SSH and switch them back on using wake on none by putting a pi0 in the local area networks of the JSON Nano, JSON Orins, etc. And we are also measuring the time and energy that is needed during the switching on and off procedures. We have a video here at this QR code of us switching on and off the nodes. And then we are deploying everything over real smart grids. We have one smart grid using wind turbines in Aalborg, one that you are building using photovoltaics, and we are creating a platform that mixes together simulated nodes, simulated microgrids, and real environments. Obviously, we cannot anymore do in the 30x speed up, but this is for sure an improvement in terms of realism. And finally, in the future, we plan to open the platform to receive real-world workloads from, for example, the students of our university, for example, LLM interrogations, queries. We plan to study workload diversity. For example, some workloads with need GPUs will be memory intensive. And we will study the trade-off between the OPEX, in general, the saved energy, and the CAPEX, how much we need in terms of money to create the microgrids. And also, we consider smart grid operations. The microgrid that will predict how much energy it needs tomorrow to buy it on the day-ahead market. I am Michele Albano. I am from the Distributed and Sustainable Software and Systems Research Group at Open University. And you can see here the QR code to my social networks. Thank you for your attention.